Hello everybody, I'm Adam. In this problem, we're going to be evaluating our integral of the function t squared divided by the quantity 1 minus t squared to the 3/2 power from 0 to root 3 over 2. And we're going to evaluate this using A, our given integration limits that we have over here, and then also the limits obtained through trigonometric substitution. So before we get to the evaluation part, we need to first find the antiderivative. So the first thing we're going to do is find the antiderivative of our function t squared divided by the quantity 1 minus t squared to the 3/2. So if we take a look at this, right, this is one of the classic problems that says that we need to use trigonometric substitution to find the antiderivative. And how do we know this? Well, if we namely look at the denominator, the 3/2 power, or the half power, tells us we have a square root. And whenever we have a square root of something looking like some constant squared, say a squared, minus a variable term squared, say u squared. Now, of course, this 3/2 can be written as this square root cubed, but we still have the square root term. So that says we can use trigonometric substitution, and in this particular form, a squared minus u squared, we can use the substitution of u equal to our constant a times the sine of theta. So that gives us a place to start. So to start with, we're going to make our substitutions. So in this case, our variable term u is just t. So t is equal to a sine theta. Well, our a, right, 1 being 1 squared, a is just 1. So t is just 1 times sine of theta, or sine of theta. And so we need to substitute all our variable terms out. So t is sine of theta. Then dt, taking the derivative of both sides, is going to be equal to cosine of theta d theta. And lastly, our square root term, square root of 1 minus t squared, is equal to the cosine of theta. So now that we have this, we're going to plug everything into our integral. So again, we're taking the indefinite integral here, just finding the antiderivative. So we have the indefinite integral of t squared divided by, I'll write it, quantity of the square root of 1 minus t squared cubed dt is equal to the indefinite integral of, and make our substitution. So t is equal to sine, so t squared is going to be sine squared theta. Our square root term on the bottom is equal to cosine. So on the bottom we'll have cosine theta cubed. And then our dt is equal to cosine theta d theta. Okay, so once we get everything plugged in, we'll see what we'll simplify. Well, we notice we have a cosine here, which will cancel with 1 cosine on the bottom, leaving us with cosine squared. So we have sine squared over cosine squared, which is equal to indefinite integral of, we can write it as tangent squared theta d theta. Okay, and where do we go from here? Well, we know we can take the antiderivative of just tangent, but not tangent squared. However, in previous sections, we've dealt with something like this, where we can use one of our trig identities, namely one of our Pythagorean identities, that 1 plus tangent squared theta equals secant squared theta. And how does this help us? Well, we know we can take the antiderivative of secant squared, which is equal to tangent. So we can actually write this integral of tangent squared. All right, so what would tangent squared be equal to? If we subtract 1 from both sides, we have the integral of, instead of tangent squared, secant squared of theta minus 1 d theta. Okay, and like we said, we can take the antiderivative of this. So antiderivative of secant squared is tangent of theta, and then antiderivative of minus 1 with respect to theta is just going to be minus theta. And of course, at this point, we have plus some general integration constant c. Okay, so this is our first antiderivative as a function of theta. But what we want to find is the antiderivative as a function of t. So we have to substitute back in our trig values and thetas for functions of t. So what do we have here? Well, looking at tangent, right, tangent of theta we know is sine theta over cosine theta. Well, what do we have here? Sine theta is equal to t, and cosine theta is equal to the square root of 1 minus t squared. So tangent of theta is equal to t divided by the square root of 1 minus t squared. So that gives us our tangent theta part. And what about theta? Well, once again, we know that t is equal to sine theta, or sine theta is equal to t. And so taking sine inverse of both sides would solve for theta. So theta would be equal to arc sine, if you prefer, or sine inverse of t. So now we can make our substitution in here and get our antiderivative as a function of t. So again, for tangent, we have t divided by the square root of 1 minus t squared minus theta, or minus sine inverse of t, and plus our general integration constant c. So now as we move into parts A and B, we're going to be using both of these. Okay? So now let's take a look at part A. We're going to evaluate the antiderivative with our given integration limits. So all the way back to the original problem. So we're going to evaluate the antiderivative as a function of t with our limits from 0 to root 3 over 2. So, all right. So for part A, so we're taking our definite integral from 0 to root 3 over 2 of our function t squared over the square root of 1 minus t squared cubed dt. Right? And so this is equal to evaluating our antiderivative. So our antiderivative as a function of t is the quantity t over the square root of 1 minus t squared minus sine inverse of t. Now, since we're evaluating the definite integral, we can go ahead and drop our integration constant. And we'll evaluate this from 0 to root 3 over 2. Okay. All right, so how do we do this? Well, take the upper limit, plug it into our function, and subtract everything with the lower limit plugged in. So plugging in root 3 over 2. So in for t, we're going to have root 3 over 2 divided by the square root of 1 minus quantity root 3 over 2 squared minus the sine inverse of root 3 over 2. Okay, and then that's subtracting with the quantity plugging in 0 for everything. Well, with this we can save ourselves a little bit of work. If we plug in 0 for t, that's 0 in the numerator, and 0 in the denominator just gives us 1, so we're defined there. So the first term is just 0, and then minus sine inverse of 0 is also just 0. So we get 0 minus 0, or 0. And okay, so we'll just focus on this part. So we're equal to, well, coming up here, squaring root 3 over 2 will give us, say, 3/4. So we'll have root 3 over 2 over the square root of 1 minus 3/4, which is the square root. 1 minus 3/4 is 1/4, and the square root of 1/4 is just 1/2. And minus sine inverse of root 3 over 2 gives us pi over 3. Okay, and here we have root 3 over 2 divided by 1/2. Inverting and multiplying, our 2's would cancel. in our denominator, so leaving us with root 3 over 1, or just root 3 and minus pi over 3. So there's our value in exact form. As an approximation, we'll use our calculator. Okay, so square root of 3 minus pi over 3 gives us approximately, say, 0.685. So there's our definite integral evaluated at our given integration limits. So now what we're going to do for part B is evaluate the integral at the limits obtained by trigonometric substitution. What does that mean? Well, what that means is, I said we're going to look at both of these antiderivatives over here. We're going to go to the antiderivative as a function of theta and see what our t limits would be in terms of theta and evaluate that. Meaning, we have our lower limit, t equal to 0. Well, that implies, what is theta? Theta is, as we found, sine inverse of t, or sine inverse of 0, which is equal to 0. So when t is equal to 0, theta is equal to 0. And when t is equal to, say, root 3 over 2, that implies that, oops, all right, theta is equal to sine inverse of root 3 over 2, or sine inverse of root 3 over 2 is pi over 3. So our two upper and lower limits, lower limit is 0, upper limit at theta is pi over 3. So once again, this definite integral from 0 to root 3 over 2 of our original function t squared divided by the square root of 1 minus t squared cubed dt is equal to evaluating the antiderivative as a function of theta, right, tangent theta minus theta. Again, we can drop the integration constant, and evaluating this from the lower limit 0 to the upper limit pi over 3. Okay, so again, plugging in our upper limit, we have tangent of pi over 3 minus pi over 3. And then minus plugging in 0, tangent of 0 is 0, and plugging in 0 for theta, we get 0. So this is minus, again, 0 minus 0, which is just 0. So all we have is tangent of pi over 3 minus pi over 3. And the tangent of pi over 3 is just root 3 and minus pi over 3. Which should come as no surprise, which is what we got in exact form from our first evaluation. So we have root 3 minus pi over 3, which again is approximately positive 0.685. So there we have our definite integral using the limits obtained from trigonometric substitution. Thank you very much.